Let's talk about thermochemical equations. Thermochemical equation is a chemical equation for a reaction, including the physical states, which is very important, in which the equation is given a molar interpretation and the reaction enthalpy for these molar amounts is written directly after the equation. So in essence, it's a normal reaction with a delta H quantity behind it. Now, why is it important to do the physical states? That's because the physical states tell you which equation you're dealing with. The delta H of the formation of water liquid from hydrogen gas and oxygen gas is not the same as for the formation of water gas. So the phases are very important when you're trying to determine the delta H's of different reactions. So let's look at this reaction. I have 1 mole of N2 gas plus 3 moles of hydrogen gas gives me 2 ammonia gases. Just like we did before, balanced equation, except now it has this delta H behind it. Okay, this is telling me the heat associated with this reaction. Since this is a negative 91.8, this is telling me this is an exothermic reaction. Heat is released. It's important to realize that that negative sign is just telling me it's an exothermic and the heat is being released. It's not a negative sign. It's just telling me that it's an exothermic reaction and that heat is being released. 91.8 kilojoules of heat is released in this reaction. Now, since enthalpy is an extensive property, this means that the value of the reaction enthalpy is directly proportional to the amount of the reactants and products involved in the reaction. This equation basically gives me a recipe of what and how much to mix. If I take 1 mole of N2 and 3 moles of H2, it will produce 2 moles of NH3, but in the process, it will release 91.8 kilojoules of energy, of heat. Since enthalpy is an extensive period, if we change the recipe, then the amount of heat generated will vary as well. So if I halved everything, say I took a half a mole of N2 and took 1.5 moles of H2, I would only form 1 mole of NH3. Well, since I have half the reactants and forming half the products, I'm going to form half the heat. So there'd be 91.8 times 1/2 as well. That would be the amount of heat that is generated, that is being released. Since enthalpy is an extensive property, we can set up conversion factors based on the coefficients and the delta H values in the thermochemical equation and perform calculations similar to stoichiometry calculations. Going back to our reaction, this reaction, there are conversion factors within this reaction. I can say there's 91.8 kilojoules of heat released per every 1 mole of nitrogen gas being consumed. Now, once again, this is just telling me that heat is released. It's not really a negative sign. Telling me it's an exothermic reaction. Okay, we're going to do the 91.8 kilojoules of heat released per 3 moles of H2 being consumed. We also have 91.8 kilojoules of heat being released per every 2 moles of NH3 formed. So we have these conversion factors. We can use them this way or we can use them the other way. Once again, they're equal to 1 in the sense that if I have 91.8 kilojoules of heat, then I know I have 2 moles of NH3 being produced. If the delta H of a reaction is X, then the delta H for the reverse reaction is minus X. If a reaction is exothermic, its reverse reaction is endothermic, and vice versa. So what we're saying is if you have the reaction and you know the heat associated with that reaction, if I flip that reaction, the opposite reaction will be the opposite amount of, the same amount of heat numerically, but the opposite sign, meaning if it was exothermic, now it's endothermic. Same magnitude of delta H, but the algebraic sign will be reversed. Example, I have 2 hydrogen gases plus oxygen gas gives me 2 water gases. The heat associated with this is 483.7 kilojoules of heat being released. Exothermic process. However, if I take the equation and flip it, now I say I got water gas being decomposed into hydrogen gas and oxygen gas, then the delta H still equals 483.7 kilojoules of heat. However, now it's a positive sign indicating that it's being absorbed, meaning it's an endothermic process. If one process is exothermic, the opposite must be endothermic, and vice versa. When a thermochemical equation is multiplied by any factor, the value of delta H for the new equation is attained by multiplying the delta H in the original equation by the same factor. Remember, this is an extensive property. Therefore, if I have half the amount, then I get half the heat. Well, if I multiply by any factor in my equation, I got to multiply that factor to delta H as well. Look at this example. I got 2 H2s plus O2 gives me 2 waters, and delta H is 483.7 kilojoules. Negative telling me that it's being released. If I happen to multiply this same equation, see I got 2H2 multiplied by 2, multiply the oxygen by 2, and the 2 waters by 2, so now I got 4, 2, and 4. That means I also have to multiply my delta H. So in essence, we're looking at here 483.7 times 2. Which is 967.4 kilojoules. I'm doubling the recipe, doubling the heat that's being released. Note, in each one of these examples here, I have this little superscript 0. Okay? This indicates that we have thermodynamic standard conditions. Okay, what are thermodynamic standard conditions or standard state? That's 25 degrees C, 298 Kelvin, 1 atmosphere. Now don't confuse this with STP, standard temperature and pressure. Standard temperature and pressure was 0 degrees C in 1 atmosphere, or 273 Kelvin. This is 25 degrees C, what we do normally at room temperature as we do in reactions. Okay, so with the gases, STP, 0 degree, 273 Kelvin, 1 atmosphere. With the thermochemistry, 25 degrees C, 298 Kelvin, 1 atmosphere. Let's look at an example. This is a stoichiometry problem dealing with heats of reaction. Consider the reaction of methane burning in the presence of oxygen at constant pressure. Given the following equation, how much heat could be attained by the combustion of 10 grams of methane, 10 grams of oxygen, and then 10 grams of each? What we're doing here is we're showing the first one in red here, the 10 grams of methane, and just doing the calculation assuming that oxygen is in excess. Okay, is what we're doing with the first one. Then we're doing the same problem again, but we're going to assume methane is in excess and say we have 10 grams of oxygen. How would that affect the amount of heat? And then we're saying, oh, what if we have both of them? Then we have what we call a limiting reagent problem. You might recall doing that a couple of chapters ago. Okay, so we need to find out which one's going to run out first, and that's going to dictate how much heat can be produced, or well, in this case, would be released, since we got the negative sign. Notice that this has a negative, which means this is an exothermic reaction, and that heat is released. So let's do the first one. We will determine the amount of heat by performing a stoichiometry calculation similar to what we did earlier sections, except that we use a conversion factor involving the heat. We'll convert the mass to moles, and then that moles to kilojoules of heat. So for part A, let's call this part A. Okay, I have 10 grams of my methane, my starting point, assuming that oxygen is in excess. So we assume oxygen is in excess. Okay, so from here, I got to go from grams to moles. So here I have my molar mass of my methane, 16.04 grams methane to 1 mole. Have my grams cancel. And then I got to have my conversion factor between methane and my heat. Well, there's 1 mole of CH4 to 890.3 kilojoules released. units cancel, moles and moles, multiply it through, tells me I got 556 kilojoules of heat being released. That's the answer to the first question. Let's do the second question. Second part of the problem will be conducted the same way, but now we're using the oxygen factors. So, for part B, we are assuming methane is in excess. Okay, so we start off with our 10 grams of oxygen, molar mass of oxygen, 32 grams of oxygen for every 1 mole, so I have my units of grams cancel. And we're talking about its relationship. Well, there's 2 moles of oxygen to 830.3 kilojoules of heat being released. So we set that up, our relationship. 890.3 kilojoules of heat released per every 2 moles. Multiply it out, I get 139 kilojoules of heat being released. That's the answer to number 2. Now, the third one, C, is assuming now that we have 10 grams of each. So that's like, okay, we're assuming 10 grams of methane and 10 grams of methane and 10 grams of oxygen. So we need to find out which one's going to run out first, because that's going to dictate how much heat can be released. Once one of the substances runs out, the reaction can't go anymore. Okay? So we don't have to calculate it because we already did both of them. So what we're going to do is look at these 2 numbers, and the one with the smaller amount of heat is going to be the final answer and dictate which one is our limiting reagents. Well, oxygen has a small amount of heat. You got 139 kilojoules of heat versus 556 kilojoules of heat. From the methane. Well, we're obviously forming less heat with the oxygen, so therefore my oxygen is my limiting reagent. And my final answer is my 139 kilojoules of heat, and I got to put my minus sign to indicate that it's being released. You can say, well, you got to look at the numeric number, not the sign. Remember, the sign's only telling me if it's being released or being absorbed. So we're just looking at the numeric number, and 139 is a smaller numeric number than 556. Since O2 is generating less kilojoules of heat, it is the limiting reagent, meaning that your 139 kilojoules of heat released is also the answer to part 3 as well. Should be able to do homework 52, which involves some stoichiometry problems involving heats or reactions. I think the last couple are limiting reagent problems.